Welcome to this TIA Connect demonstration. We will see how to analyze and understand a legacy PLC program, a poorly commented program, with cryptic tag and block names, developed by multiple contractors at different times. This is exactly the type of program found on most industrial production sites. Our demonstration project is called FruitLine Demo. It simulates a concentrated fruit syrup production line, raw material reception, blending, heating and pasteurization, additive dosing, filtration and CIP cleaning. The project contains 29 PLC blocks, 62 tags and 5 HMI screens. Less than 10% of the code is commented. Block names are misleading, for example, FB_control_1 gives no indication of its actual function. This is a typical legacy program. First capability, block explanation. We will ask TIA Connect to explain blocks whose names reveal nothing about their function. First scenario. We ask, what does FB_control_1 do? The name gives no indication. Let us see what TIA Connect will answer. The copilot analyzed the code and identified that FB_control_1 is actually a proportional temperature controller. It scales a raw analog signal over a range of 0 to 150 degrees, calculates an error against the setpoint, and applies a proportional gain configurable via db_config.param3. The output drives a valve between 0 and 100%. The block detects when the temperature reaches the setpoint within a tolerance band defined in db_config.param4, then starts a hold timer. It also includes an over-temperature protection at 130 degrees that shuts off the valve if exceeded. All of this inferred solely from the code, without any comments. Second scenario. We ask for the explanation of a specific network 3 of block FB_process_A. Once again, the block name reveals nothing. Let us see what TIA Connect identifies. The copilot identified that FB_process_A is a blending sequencer written in SCL, with a 6-step state machine in a single network. Network 3, which corresponds to step 3 of the sequence, is a timed hold of 60 seconds. During this hold time, the block continuously reads the parameter db_config.param1 into a local variable. Once the 60 seconds have elapsed, the timer is reset and the sequence advances to step 4. This explanation is generated entirely from code analysis, no comments were present in the original program. Second capability, dependency tracing. We will follow the usage of a tag across the entire program, both PLC and HMI. Third scenario. We ask, which blocks use the tag TT_pastor_in? We first called the direct cross-references, which show that this tag is read in OB35 and in OB1. Let us now see what the copilot adds with its contextual analysis. The copilot confirms that TT_pastor_in is an analog input tag at address IW64, read in 2 blocks, OB35 for the fast cyclic task and OB1 for the main program. No block writes to this tag, which is consistent with a temperature sensor input on the pasteurizer. Any modification to this tag or its addressing impacts both blocks. Fourth scenario. We open db_config, a data block with 30 variables named param1, param2, up to param30. No documentation, no comments. We ask, where is param7 used, and what does it correspond to? Let us see the answer. The copilot analyzed the cross-references of db_config.param7. Interesting result, param7 is initialized at startup in OB100, but is not read by any block in the program. The copilot proposes 3 hypotheses: either it is a parameter reserved for future use, or it is dead code from a removed feature, or the value is read directly by the HMI via a binding without going through the PLC logic. It recommends checking the HMI bindings and documenting the parameter. This is no longer a simple reference search, it is a contextual analysis that gives meaning to opaque variables. Fifth scenario. We ask for the complete call tree from OB1. Let us see how TIA Connect maps the program structure. The Copilot reconstructed the complete call tree from OB1. 11 networks in total, 9 function block calls and 2 inline code sections. The execution order starts with FB_SEC for safety, then FB_RCV pump for the feed pump, FB_tank level for level control, FB_process_A for the blending sequencer, then a hard-coded interlock in network 5, a duplication of the safety logic already handled by FB_SEC, typical of a legacy modification. Then FB_control_1 for heating, FB_AUX_dose for dosing, FB_filter manager for filtration, FB_cleaning for CIP, and finally FB_alarm manager for alarms. The Copilot also detected that network 5 duplicates the emergency stop logic. This is exactly the type of structural anomaly found in legacy programs. Third capability, impact analysis. What happens if we modify a parameter? This is the question every automation engineer asks before touching a legacy program. Sixth scenario. We ask, what happens if we modify the setpoint stored in db_config.param1? What is the complete impact chain? Let us see the analysis. The Copilot traced the complete impact chain of db_config.param1. First, this parameter is initialized to 100 in OB100 at every CPU restart, so any online modification is lost at the next restart. Then, param1 is read by FB_process_A at step 3 of the blending sequencer, during a 60-second window. The value is captured in a static variable rval1, but this variable is never used in the rest of the code. It is potentially dead code or an unfinished feature. The Copilot also notes that param1 is not on the safety critical path, and is not directly exposed on the HMI either. This analysis is assisted by artificial intelligence. Final validation remains the responsibility of the engineer. Fourth capability, process zone classification. We will show how TIA Connect identifies blocks related to a specific process and how the result improves with external documentation. Eighth scenario. We ask, which blocks are related to the CIP process? For now, no external document is loaded in the custom knowledge base. Let us see what TIA Connect identifies solely from the code. Without external documentation, TIA Connect identifies FB_cleaning as the primary CIP sequencer, 4 steps, pre-rinse, caustic wash, acid rinse, final rinse. It also detects the interactions. FB_control_1 is disabled during CIP, FB_SEC receives the CIP active state, and the duration of each phase comes from db_recipe. The result is correct but based solely on the code. Let us now see how the result improves with a process document. Now, we will add a process document to the TIA Connect custom knowledge base P&ID of the plant CIP circuit. This document describes the equipment, valves, and connections of the cleaning circuit. Once added, TIA Connect will automatically index it and can cross-reference it with the PLC code. We ask exactly the same question, which blocks are related to the CIP process? This time, the P&ID of the CIP circuit is available in the custom knowledge base. Let us see if the result is different. With the P&ID available, the Copilot enriches its analysis. It still identifies FB_cleaning as the main CIP sequencer with its 4 phases, and the interactions with FB_SEC and FB_control_1. But this time, it can cross-reference the PLC code with the process documentation. The valves, equipment and connections of the CIP circuit are now identifiable.
This is the added value of the custom knowledge base, cross-referencing PLC code with process documentation for a more complete understanding of the plant. Fifth and final capability, safety interlock identification. Finding all safety conditions in a legacy program is critical and particularly difficult when the code is not properly structured. 10th scenario. We ask, what are the safety interlocks in this program? And we specify, check all blocks, not just FB_SEC. Let us see what TIA Connect detects. The Copilot performed a complete audit of safety interlocks, analyzing the 26 program blocks. Here are the main results. The block FB_SEC is the centralized safety manager. It handles the emergency stop, the safety door, overpressure, and the safety relay. It feeds a master signal, db_sec.master_enable, which acts as a global lock for the entire plant. Each function block integrates its own protections. FB_RCV pump monitors dry run and overload, FB_tank level controls high and low levels, FB_process_A limits temperature and time overruns, FB_cleaning ensures process isolation and mutual exclusion. The architecture is therefore two-tiered, a centralized lock via master enable, and local protections distributed in each process block. Let us now move to the critical tag ranking. We ask the Copilot to analyze all project tags and rank them by criticality. For each critical tag, it must specify its name, data type, the blocks that use it, and the reason for its criticality, safety, process control, or fault management. The Copilot analyzed the 62 project tags and ranked them by criticality. At maximum priority, the safety tags, ES_emergency, the main emergency stop, and B_input_08, the zone 2 emergency stop. These two tags feed FB_SEC and trigger a total line shutdown. The Copilot also flags that B_08 carries a generic name, which constitutes a documentation risk. At second priority, the process safety tags, TT_Pasteur_in, the pasteurization temperature, and Pasteur_Tempoke, the interlock between temperature control and dosing. At third priority, the production status tags, line_running, used in 6 out of 11 networks in OB1, and CIP_active, which ensures mutual exclusion between production and cleaning. Then come the fault tags such as feed pump_fault, the level sensors LS_tanke_high and low, the flow rate FT_feed for dosing accuracy, and the differential pressure filter_DP_high. The Copilot also identified a potential risk. No explicit mutual interlock is visible between auto_mode and manual_mode at the OB1 level. Let us recap the 5 analysis capabilities we demonstrated in this tutorial. First, block explanation. The Copilot analyzed the structure and logic of individual blocks such as FB_SEC, describing their role and behavior. Second, dependency tracing. We saw how the Copilot traces call chains to identify which block calls which, such as the chain from OB1 to FB_control_1 to FC_temp scaling. Third, impact analysis. The Copilot evaluated the consequences of modifying a block, identifying all cascading affected blocks and tags. Fourth, process classification enriched by the custom knowledge base. By adding a P&ID document to the custom docs folder, the Copilot was able to classify blocks by functional area with significantly higher precision. And fifth, safety audit and critical tag ranking. The Copilot identified all safety interlocks distributed throughout the program and ranked tags by criticality, from emergency stop to operating modes. This tutorial is now complete. We have seen how TIA Connect enables in-depth analysis of an existing PLC program, without prior documentation, in just a few minutes. Whether it is to take over a legacy project, audit the safety of a plant, or simply understand how an unknown program works,
the integrated copilot offers valuable assistance to automation engineers. Thank you for watching this presentation.